Hello everyone, welcome to the video. Today we are going to solve the problem coin change, minimum number of coins required. In this problem, we are given an array. Each element of array represents a coin or a note of a particular denomination in a currency. For example, this array represents that we have a 1 rupee coin, we have a 2 rupee coin and we have a 5 rupee coin. We are given that for each of these denomination we have infinite supplies of coins. Basically we have infinite 1 rupee coin, we have infinite 2 rupee coins and we have infinite 5 rupee coins. Then we are also given an amount. Our aim is to form this amount using these coins. But the constraint is that we have to minimize the number of coins that we use. And as answer, we have to return the minimum number of coins that we used. In the previous video, we solved the same problem using the recursion and top-down dynamic programming approach. In this video, we will solve this problem using the bottom-up dynamic programming approach. We'll go through the thinking process, we'll write the algorithm, and then we'll also see a code walkthrough for the same problem. We'll also see how do we calculate the actual coins used using the bottom-up dynamic programming approach. But before we start, if you are new to this channel, please don't forget to subscribe and click the bell icon. Let's start. To begin with, let us first note down the key things given in the question. We are given that we have infinite supply of every denomination of whatever coins are available to us. We are also given a target amount n, and we have to form this target amount using these denominations. But the constraint is that we have to minimize the number of coins that we use to form the target amount. So if we consider an example, let us say we are given a denominations of 1 rupee coin, 2 rupee coin and 5 rupee coins. And we have to form the amount n is equal to 11. So our answer will be 3. Why? Because we will use minimum of 3 coins, 5, 5 and 1. So if we consider our solution as a black box, we are getting a denominations array as an input. We are also getting a target amount n as an input, and we have to return the minimum number of coins. So what will our function signature look like? Our function signature may look something like this, or it may look something like this. In the first case, the denominations array is also part of the input that is given to the function. But in the second case, denominations array is not part of the input. This may happen when in the question we are told that denominations are fixed, and with every run of the program only the n input will be modified. Denominations won't be modified with every input. But in either case, both of these will have similar solution approaches, so it won't matter much. Before we move to the bottom-up approach, let us briefly recap how did we solve this problem using top-down dynamic programming approach. So first of all, we tried to see if we could use the answers to smaller problems to derive the answer for our larger problem. So our aim was to form the amount 11 using these denominations 1, 2 and 5. So we thought, how can we break this down into just next smaller problem? So one way was that we could just first pick 1 rupee coin and then see what will happen. So if we picked 1 rupee coin, the remaining amount with us became 10. Now if somebody told us the answer to this 10, can we use this answer to derive the answer for 11? That was the thing we were looking for. So if somebody told us that answer for 10 was m, then we knew that answer for 11 would be m plus 1, because for forming 11 we just need to pick one more 1 rupee coin. But that was just one way of breaking this problem down. We could have similarly picked a rupee 2 coin or a rupee 5 coin. In those cases, our smaller problems would become 9 and 6. And if somebody told us answers to these smaller problems as well, we can have the answer for 11 as well, n plus 1 and o plus 1. But which of these should we choose for as answer for our 11? Since we are looking for minimum number of coins, we will choose the minimum of the 3. Thus, we were able to use the answers to smaller problems to derive the answer for our larger problem. We formalized this into our recursive relation. And what did recursive relation say? It said that we will go through each of these denominations. Then our smaller problem will become n minus the denomination value. Then the answer for the smaller problem will be minimum coins n minus that denomination value. Now what will be the answer for the original problem? It will be minimum coins n minus denomination value plus 1. But this is just the candidate answer. This may not be the final answer. The final answer will be minimum of all these values possible for all possible denominations. So this was our recursive relation. So using this recursive relation, we tried to write down the algorithm. The algorithm looked something like this, that we were iterating over all denominations and we were finding the answers to our smaller problems. And for our smaller problem, we were deriving the candidate answer. And we were keeping track of what was the minimum of all possible candidate answers. But here there was a problem. This would go into an infinite recursion. There was no way this would terminate. So we needed something called as base or terminating condition. Now the base or terminating condition corresponds to that input for which we readily know the answer. Now what is such input? That input will be n equal to any of these denominations value. Because if n equals any of these denominations value, then we know we just need to pick that denomination coin and minimum coins used will be 1. So that was the base condition. Another thing about base condition is that the base conditions should be exhaustive. That means we may start with any input, but after going down the recursion path, it should end at one of the base conditions. So this n equal to any of the denominations value satisfied this condition as well. So we added this base condition. Now our algorithm was complete, but it was still exponential time complexity. Why? Because there were many overlapping problems. So how did we solve the problem of overlapping problems? We used a map. What did we do here? Whenever we encountered an input for the first time, any n for the first time, we solved it, and before returning the answer, we stored its answer in a map. Now whenever we encountered the same input for second time or any number of times after that, we didn't solve it again. We simply checked that in the map and returned the answer from the map. So this brought down our time complexity drastically to big O of n. Now this completed our top-down dynamic programming approach to this problem. Now we need to think about the bottom-up approach for this problem. But why do we need to think about the bottom-up approach itself? Is there a problem in the top-down dynamic programming? The problem is that this approach uses recursion, and therefore there are a lot of method calls. And every method call occupies some space in the memory. So since there are a lot of method calls, due to recursion, a lot of space is occupied in the memory. So it would be great if we could solve this problem in the same time complexity without using recursion, because then number of method calls will be less and hence the space occupied will be lesser. So that is why we are thinking of the bottom-up approach. Let us now see how do we even start thinking about the bottom-up approach. In top-down approach, we started from larger input, and as we went through every step of recursion, our input became smaller and smaller till we reached the smallest input or we reached the base condition. In bottom up, we will go in reverse order. We will first calculate the answers to smaller problems, then using them we will build and reach gradually to the larger input which was asked in the question. We will still use the insight of the recursive relation. We will still use the answers to smaller problems to derive the answers for larger problems, but the order will be in reverse. That means we still have to store the results of smaller problems somewhere. So The information that we want to store looks something like this. We want to store that, hey, for this number n, this is our answer. Now what kind of data structure would suit best to store this? In top-down dynamic programming approach, we used map data structure to store this information. But here, we also need to go iteratively from smaller input gradually till larger input. We can use a map here also, but it is a bit less intuitive to iterate or travel in a particular direction using a map data structure. So let us think of some other data structure that we can use to store this similar information. We can simply use a one-dimensional array with n with the key as indices and value as the answer. So here is our one-dimensional array. Every index of this array denotes an amount, a target amount that we want to form using the denominations. So the array indices are in the range from 0 till n, and the value at any index will correspond to the answer for that target amount, meaning the value at any index will tell us what is the minimum number of coins that we need to make the amount which is equal to the index. So if in the problem the input given to us is n, then in this array where will our final answer lie? It will lie here at the last element. So if we are calling this array by dp, then our final answer is basically dp of n. Now let us see what is the size of this array that we will need to declare. Since the last index is n, the size of the array will be n plus 1. Now it is clear that we have to fill this array. Now in which direction should we fill it? How do we fill it? In which order should we fill it? We know that we have to move from smaller input to larger input. So smaller input corresponds to the left side of the array and larger input corresponds to the right side of the array. Therefore, we will fill this array in left to right manner. So it is clear that we are filling this array from left to right. But how do we even start filling it? We will at least need the answer to the first element. So let's see what does the first index correspond to. The first index means our target amount is 0. So we have to form our target amount 0 using these denominations. Is there a possibility of forming this amount? No. So what will be the minimum number of coins for forming 0 using these? It will be 0 because there is no possibility of forming this amount. So we will fill here 0. Now we need to fill the remaining array. How will we fill the remaining array? Let us consider any particular element. Let us say that we want to fill the value at any index j. I have represented this array here for better viewing. Now we want to fill the value for index j. That means our target amount is j. So let us see how can we use this recursive relation to fill the value at index j. This j corresponds to n here in the recursive relation. So what will we do as per the recursive relation? We will iterate through all possible denominations like here 1, 2 and 5. So let us say we picked any denomination which is denomination I in any iteration. Now our smaller problem will become n minus denomination I. Now n corresponds to j here, so our smaller problem will become j minus denomination I. That means our smaller problem lies to the left of j. Let us say j minus denomination I corresponds to this index. Now we need answer for this smaller problem. But since we are filling this array left to right, that means we will have already filled the value at this index. So the value at this index is the answer for smaller problem. Then what will be our candidate answer? Our candidate answer will be this smaller answer plus 1. Why are we calling this candidate answer? Because this corresponds to one of the denominations. Our final answer will be minimum of all the candidate answers. So we will have candidate answer corresponding to this denomination. But there are multiple denominations. So for all of such denominations, in the same manner, we will calculate the candidate answer. But our final answer is the minimum of all candidate answers. That means when we are calculating the candidate answer, we also need to keep track of what is the minimum value among all these. So we will keep track of this minimum value in some other variable. And then whatever will be our minimum value, that will be our answer for index j. So we will fill that value, the minimum of all candidate answers, in this index. In this way, we can fill the value at any index j for this array. That means we can fill this array in this manner. So we will know what will be our final answer. So that is our rough solution approach. Now let us try to formalize this approach into algorithm. Let us see how do we convert our solution approach into algorithm. So first of all, we will declare a one-dimensional array dp of size n plus 1. We will also fill its first index value with 0. Now we know that we have to fill this array one by one from left to right. That means it is clear that we have to iterate over this array. In every iteration, we have to fill the value at that index. But to fill the value at that index, we have to also go through all the denominations. So that means we will have to iterate over the denominations as well. So we will iterate over all the denominations. And now we know that only those denominations are worth considering whose value is lesser than or equal to the target amount that we are trying to form using those denominations. So if we were iterating over the dp array using a pointer j, and if we are iterating over the denomination array using a pointer I, this is the condition that we need to check. Now if this condition is satisfied, what do we need to do? We have to find the answer for smaller problem. So since we know j, our target amount, and we know the denomination value, we know what is the remaining amount for which we are looking the answer for. So our remaining amount will be j minus denomination I. Now we want to know what is the answer for this remaining amount. So we will know that answer using the dp array. We will get dp remaining amount as the answer for remaining amount. Now the candidate answer for n for which we are looking for, it will be answer for remaining amount plus 1. Now as we iterate through all possible denominations, we will have multiple candidate answers. But we also need to keep track of what is the minimum candidate answer. So we will keep track of that in dpj variable itself. So we will initialize dpj with maximum infinity value, and at every stage whenever we get the candidate answer, we will check if this candidate answer is less than what is currently stored in dpj. If it is less, then we update the dpj. This way dpj will be minimum when we complete through all iterations for all denominations. So this way we can fill every element of the index, and when we are done with these all the iterations, we can return dpn, which will be our final answer. This approach of tracking a maximum value or a minimum value is very common. We initialize a variable with an extreme, and then whenever we find a candidate which is lesser than the current minimum or greater than the current maximum, we update the current minimum or current maximum. So this way we have overall through this algorithm, by returning the dpn, we have solved this problem using the bottom-up approach. However, there can be an extension to the problem as well. So far, we have been focused on returning what is the minimum number of coins that are required to form a value n. We could also be asked to return the actual coins that were used to form the value n and not just the minimum coins. Then we won't be returning an integer from our function, but we will be returning a list of integer from our function, and every element from that list will denote the coin used one of the coin used to form n. So if we are talking about the denominations 1, 2 and 5 and target value 11, then we have to return this list containing 5, 5 and 1 because these three coins were used to form the value 11. Let us see how can we solve that. Now, when we were calculating the minimum coins here, did we have any information about what are the coins we are using? Yes, we had. When we were here, we had multiple candidate answers. Every candidate answer corresponding to a different coin that we were using. But we were choosing only one of the candidate answer. And we were choosing that candidate answer which gave us the minimum number of coins. So when we are choosing candidate answer, in a way, we are also choosing the coin being used, the first coin being used, because a candidate answer is corresponding to a denomination that is being used. So it would be great if we could store this information that for amount n, this was the first coin we chose that corresponded to a particular candidate answer. We can use another one-dimensional array to store this information. Every index of this array will correspond to a target amount that we are trying to form. And the value at every index will correspond to the first coin that we pick to form this n. We can call this coin used array. Now let's say we have this array filled. Then can we use the values in this array to figure out what were the coins that we used for n? Let us consider the same example that we have. Let us say that our n is 11. And now let us say that in this array we had already filled that for 11 the first coin used was 5. So now can we track the remaining coins used for n? Now since we have already used a rupee 5 coin and we were looking to form rupees 11, then what is the remaining amount for us? The remaining amount for us is rupees 6. Now let's say rupees 6 corresponded to this index. Now we would have, since we have this array filled, we will have some value here as well. Now let's say that first coin used for rupees 6 was again 5. Then what is the remaining amount that we are left with? The remaining amount that we are left with is rupees 1, and we have already used two 5 rupee coins in forming rupees 11. Now let's say rupees 1 corresponded to this index. Now we will have the value filled at this index as well, and that means to form rupees 1, the first coin that we use is a rupees 1 coin. So now we have used a rupee 5 coin, another rupee 5 coin and rupee 1 coin. And what is the remaining amount that is left with us? It is 0. 1 minus 1 equal to 0. That means these are all the coins that we were looking for. Now in the question, we may be asked to return in any order, be it 551 like in this direction or 155 like in this direction. So, but it doesn't matter, we can return in any order that we want. So let us quickly summarize how did we do it. We iterated from current amount equal to n till our current amount becomes 0. And what did we do in every iteration? In every iteration, we figured out what was the coin used. We stored that coin somewhere so that we can return that in the answer. And we updated our current amount. So let us formalize this into our algorithm. So this is what our algorithm will look like. We will initialize a variable current amount with its value n. We will iterate till it is greater than 0. And in every iteration, we will figure out what was the first coin used for this current amount. We will put that coin in some stack that we have declared earlier, stack of integer. And then we will update our current amount. Then whatever the coins we've used are already present in the stack. So we will convert the stack to list in whatever order is desired, be this order or the reverse order, and then we will return it. So this way we can use this array to figure out what were the actual coins used. Now the only problem that remains is how do we fill this array. Now, as discussed earlier, we have this information here when we choose that what is the candidate answer for this particular n. When we are choosing a particular candidate answer, we are in a way also choosing what is the first coin that we are using for this particular amount. So we can store the first coin used here. In this way, we can fill our coin used array as well. It is obvious that we will have to declare this first, just like dp array. And once we are done with this part of the algorithm, we will use this to return the actual list of coins used. Now this completes our overall algorithm to return the list of coins used to form a particular amount n, with satisfying the constraint that this is the minimum number of coins used. Now what is the time complexity here? The time complexity here is big O of n multiplied by big O of size of denominations. If the denominations and size of denominations also vary with every input. But if they are constant, then our time complexity will be big O of n. And our space complexity will also be big O of n, because we are using two one-dimensional arrays of size n plus 1. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So first of all, we have these two static variables, denominations array and denominations size. Both of these are static so that we can access them outside these methods as well. We here have not considered denominations as part of the input to the function, but if we want, we can consider them as input as well. The approach does not change. So we have these variables and we are considering a wide range of denominations here for the purpose of this code. So now let's see how will the function work. So first of all, we declare a new array dp of size n plus 1. We initialize its first value with 0, because there is no way we can make change for 0 using these denominations. We also declare another array coin used that we will use to return the list of the coins actually used. Its size is also n plus 1 and its first element is initialized to -1. Why -1? Because since there is no coin we can use to form the amount 0. Now it is clear that we have to iterate. So we iterate over our array from j equal to 1 till j equal to n. We are iterating over this dp array, and our aim in every iteration is to fill the actual value of dpj. But dpj also tracks what is the minimum value among all the candidate answers. So we initialize it to plus infinity. This way, whenever we find a number which is lesser than dpj, then we will update dpj to that value. Now, to fill dpj, we have to go through all the denominations. So we go through all the denominations, and therefore in every iteration, we have what is the denomination value that we are using. Now, a particular denomination is useful to us only if it is lesser than or equal to the target amount that we are trying to make. So we have this condition. Now, if this condition is true, then we will have some remaining amount, which is positive. So this will be our remaining amount. Therefore, we can get the answer for remaining amount from the dp array here. Then when we have the answer for remaining amount, we know what will be answer for us for j using the current coin, which will be answer for remaining amount plus 1. Now if this candidate answer is lesser than the current value that is present at dpj, that means we will update dpj to this candidate answer, and that also means that we have chosen this coin. So we will update the coin used array as well. Now at the end of all the iterations, our coin used array is filled, our dp array is filled. And now if we have to return what were the actual coins used, it is pretty simple because we have the answer right here in this array. So we initialize our current amount variable with value n, and we iterate till current amount is greater than 0. In every iteration, we figure out what was the first coin used to make this amount. and we push that coin to a stack, and we update the current amount, because now current amount is equal to current amount minus current coin. So when we are done with this iteration, result stack contains only the coins that were used to form this particular amount. So then we can simply iterate over this stack, and we can put every element of that stack into a list and return it. So this is the complete code to return a list of integers that were used to form n. That list of integers correspond to the list of denominations, and we have also satisfied the constraint that these are the minimum number of denomination coins that we will have to use to form the value. Let us now run this code and see this code in action for a couple of inputs. So we'll be providing it two test cases. The first test case is n is equal to 43. Now 43 against these denominations, what can we use to make 43 in using minimum number of coins? We can use two 20 rupees coins, one 2 rupee coin and one 1 rupee coin. So let's see the answer here. It is 20, 22 and 1. Let's provide another input. Let's say 11. For 11, the answer is 10 and 1, because this is the minimum way in which we can form 11. This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also, let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.